Hello, everyone. Welcome back to our Finite Element Method lecture series. In the previous lecture, we learned how a real engineering structure is divided into small finite elements, and how these elements are connected through nodes to form a finite element model. Now, an important question arises. Are all finite elements the same? The answer is no. Different engineering problems require different types of finite elements. Choosing the correct element is one of the most important decisions in finite element analysis because it directly affects both the accuracy and the computational efficiency of the solution. Finite elements are generally classified according to the dimension of the problem they represent. Let's begin with the simplest one: 1D elements. One-dimensional elements are used when one dimension, usually the length, is much larger than the other two dimensions. Examples include bars, rods, trusses, springs, pipelines, and transmission members. Notice that these elements have only two end nodes, and the physical behavior is represented along a single line. For structural analysis, bar and truss elements are commonly used to model axial forces, while spring elements represent elastic supports or connectors. Typically, each node has 1 or 2 degrees of freedom, depending on the type of problem being solved. Next are the two-dimensional elements. These elements are used when the thickness is much larger than the other two dimensions. Examples include plates, slabs, walls, bridge decks, and shell structures. The most common shapes are triangular and quadrilateral elements. Higher-order elements with additional nodes are also available whenever higher accuracy is required. These elements are widely used for problems involving plane stress, plane strain, heat conduction, and fluid flow. Normally, every node has 2 degrees of freedom, representing displacement in the x and y directions. Now let's move to three-dimensional elements. These elements represent the actual volume of a body and are used for solid structures. Examples include concrete foundations, machine components, dams, pressure blocks, and rock masses. Common 3D element shapes include tetrahedral, hexahedral, and wedge elements. Since these elements occupy space in all three directions, each node generally has 3 translational degrees of freedom in the x, y, and z directions. Finally, we have axisymmetric elements. These are used for bodies that are symmetric about an axis. Examples include pipes, pressure vessels, storage tanks, and rotating machine components. Instead of modeling the complete three-dimensional body, we only model a two-dimensional cross-section and mathematically revolve it about the axis. This approach significantly reduces computational time while still producing accurate results. So remember this simple classification. One-dimensional elements model lines. Two-dimensional elements model surfaces. Three-dimensional elements model volumes. Axisymmetric elements model bodies of revolution. Choosing the right element always depends on the geometry, the physics involved, and the level of accuracy required. Now that we know different element types, another important question comes to mind. What information is actually stored at every node? The answer lies in the concept of degrees of freedom. Let's understand that next.
Degrees of freedom, commonly called DOF, represent the independent unknown quantities associated with a node. In simple words, they describe how a node can move or rotate. These are the unknown values that the finite element method solves during analysis. Let's first understand the two-dimensional case. In a two-dimensional structure, a node can move in the horizontal direction, represented by UX. It can also move vertically, represented by UY. In addition, the node may rotate about the z-axis, represented by theta z. Therefore, a node in a plane problem can have 3 possible degrees of freedom. However, not every element uses all 3. The number of active degrees of freedom depends on the type of finite element. For example, a truss or bar element mainly carries axial force. Therefore, only translational degrees of freedom are considered. A beam element can bend, so besides vertical displacement, rotational movement must also be included. Frame elements generally include both horizontal and vertical translations along with rotation. Now consider a three-dimensional solid. A node can translate in 3 directions, x, y, and z, and it can also rotate about all 3 axes. Therefore, in a fully three-dimensional structural model, a node may have 6 degrees of freedom. One important point to remember is that degrees of freedom are always associated with nodes, not with elements. The total number of unknowns in the system depends on the total number of nodal degrees of freedom. Naturally, increasing the number of degrees of freedom increases the size of the global stiffness matrix and the computational effort required to solve the problem. Therefore, selecting the correct degrees of freedom is extremely important. Too few degrees of freedom produce an unrealistic model, while unnecessary degrees of freedom increase computational cost without improving the solution. So always remember this simple definition. Degrees of freedom represent the unknown movements or rotations at each node. Now that we know what information is stored at the nodes, let's see how engineers decide how many elements should be used in the model. This brings us to mesh generation. Mesh generation is the process of dividing the geometry into finite elements connected at nodes. The objective is very simple: create a mesh that provides accurate results with minimum computational effort. Let's first compare 3 different meshes. The first is a coarse mesh. Here, only a few large elements are used. The computational time is low, but the accuracy is also limited because the model cannot capture rapid changes in stress or displacement. Next comes the medium mesh, which provides a better balance between accuracy and computational cost. Finally, we have the fine mesh. A large number of small elements are used. This improves the accuracy considerably, but the computational time and memory requirements also increase. So there is always a trade-off between accuracy and computational cost. A common misconception among beginners is that we should always use the finest possible mesh. Actually, that is not the best approach. Instead, engineers refine the mesh only where necessary. Look at the example of the rectangular plate with a circular hole. Notice that the mesh becomes much denser around the hole. Why? Because stress changes rapidly near holes, corners, supports, and concentrated loads. These regions require more elements to accurately capture the stress distribution. On the other hand, regions where stress varies smoothly can be modeled using larger elements. This strategy provides high accuracy without unnecessarily increasing the computational cost. Several factors influence mesh density, including the complexity of the geometry, loading conditions, material properties, expected stress gradients, and the desired level of accuracy. A good mesh also follows some basic guidelines. Use appropriate element types. Avoid highly distorted elements. Gradually change the element size. Maintain smooth transitions between coarse and fine regions. And always check mesh quality before beginning the analysis. Remember the key message written at the bottom of the poster. A good mesh leads to reliable engineering results, whereas a poor mesh can produce incorrect solutions, regardless of how advanced the software is. In this lecture, we learned about the different types of finite elements, understood the concept of degrees of freedom, and explored how engineers generate an efficient finite element mesh for analysis. In the next lecture, we will continue with mesh refinement, element connectivity, and local and global coordinate systems. These topics explain how finite element models are improved and assembled before solving the governing equations. Thank you for watching. If you found this lecture helpful, please like, share, and subscribe to support the channel. Also press the bell icon so you don't miss the next part of this FEM series.